Folks, hello and welcome to week 7. Here we are 3 weeks away from finishing this up, and we have officially turned the corner here and gone from differential calculus that we studied starting with limits in the first couple of chapters or first couple of weeks of the course. And we've gone through several lessons on differential calculus. And now we're at the point where we're going to talk about integral calculus. And, you know, when we first learned to add and subtract, we realized that those are opposite functions, and the same thing with multiplication and division and exponents and roots. And that's exactly the point we're at now in calculus. We have gone through the idea of differentiation, and now we're going to go through the idea of differentiation. And there's a good little example here in your discussion post this week to sort of set that up. So everybody, please make sure you have your calculus identification number ready to go here, and we'll start this problem. So let me read this. Let me read through this with you, and we'll get started. So the volume of fuel in a tank changes at a rate given by the equation. And so let me first of all highlight the fact this is not a volume function itself. This is the rate of change of volume, which, you know, based on the last 6 weeks, you certainly would agree with me that the notation that we show here is a rate of change. It's a first derivative. So one more time here, the volume of fuel in a tank changes at a rate given by this equation for some value of time greater than or equal to 0. Now, some additional information to go along with this first, and then we'll get back to kind of the heart of the matter here. At some time t, which is going to be the square root of d, whatever your d value is in your calculus identification number. So at the square root of d hours, the tank holds 9 point b, as in that b in your calculus identification number gallons. What is the volume of fuel in the tank after c hours? And we're going to round that answer to 1 decimal point. So obviously, it looks like you need B, C, and D from your calculus identification number here, and here are some examples. So again, let me make the point here that this given function that you have here is the rate of change of volume of this tank. And again, the notation here, and I know that, you know, on a number of the discussion posts, I know I was probably pretty hard on the notation. But it is so important, especially in calculus, that you have the notation correct. You know, it's really just one of those things that you know, I harp on because it's important, not because I want to give you a hard time. But you know, as you go through the bookkeeping, you certainly want to know what each line is representing. So the notation is important. So now we're at the point where we want to take this function, and essentially what we're doing is we're going backwards. So, you know, if over here I had some function v of t, we took the derivative, we went here. So where you're at now is you're at v of t, and you want to go to this function such that you took the derivative of it and you got v of t. So in my first line here, in some, you know, offering some guidance in this discussion post, what I say to you here is I'm looking for a function v of t such that when we take the derivative of v of t, we get v prime of t, as I just sort of explained here in this little back and forth as shown above. We call this function v of t, the notation or the language that we use to associate the two is that v of t is actually the antiderivative of v of t, because when I take the derivative of v of t, I get v prime of t. So I hope I try not to confuse you here, but there is some new lingo here. And the notation to find it is this integration symbol. And so what we're going to do is we're going to integrate, or we're going to find the antiderivative of 4t over the cubed root of t squared plus 3. Notice I have a dt here that essentially in this case denotes that we're integrating with respect to t. Now, there's two types of integrals. There are indefinite integrals, which I show here, and there are definite integrals that you'll see later. A definite integral would have a value here at the bottom of the integral symbol and one at the top of the integral symbol to say that we're really at this point integrating over a certain range of the domain of this value or this variable. But in this case, we're just looking for essentially the general form of this function. And so, as we talked about in differentiation, or really, going back to things like exponents, there's a bunch of rules that go along with these techniques, and integration is no different. There are tons and tons of rules to integrate depending on the function that you are working with. And the first, typically when we start talking about integration, we, look at this idea of U substitution. And, in just a very short explanation of that, I want to just kind of focus on two terms here. You have a t squared here term, or t squared term here, sorry, and a 4t term here. And that that when you take the derivative of t squared, that you're going to get 2t, which to some degree looks like 4t, right? It's a factor of 2 off, but what's more important is they are both at that point, the derivative of t squared and 4t are both linear terms involving t, and you'll see that you can do some cancellation. And I'm just trying to sort of set up this idea of U substitution. So here's what we're going to do. We're going to use this U substitution. And this integration comes with experience. As I mentioned here, there's all types of rules that you will have. And so what you're going to do, or what I would encourage you to do, is your U substitution will be let U equal to t squared plus 3. So we're going to set up an integral here. Instead of t squared plus 3, you will have U. So what I want you to do at this point, once you have found, or once you have chosen an equality for U, I want you to take the derivative of U. So you're going to take the derivative of t squared plus 3, and we just talked about what that derivative is. And once you get du over dt, it'll be t squared, obviously. What I want you to do at that point is I want you to solve for d of t. So, treat these, again, just treat this as a ratio, and you're going to solve for d of t. Then, after these first two steps, I want you to rewrite the antiderivative subbing for u. So again, rewrite this. So you'll have 4t over the cubed root of u. And then I also want you to substitute for dt. So whatever you got when you solve for dt here, you're going to have that substitution here. Okay? And I note here, if you do this correctly, you will have a function of u. So once you have computed du over dt, solve for dt, and set up the antiderivative with u equals, this now becomes an expression totally or completely in u as the variable. Now, in the book, there is an explanation of rules for integration, and what you're going to have here, you'll see that you're going to be able to cancel some things. You'll no longer have t's, you'll have just something involving u, and it'll be u being raised probably to the minus 1/3 power. And so there are rules for integration where you can simplify that, and then you will have at that point you will have an antiderivative. And I say here, don't forget to add the integration constant. So once you do that, you'll have something involving u, and then you'll have a plus c at the end, denoting the fact that you have an indefinite integral. At that point, I want you to replace wherever you see the u, go back and replace t squared plus 3, and then you will have an equation that is the antiderivative. It'll be v of t is equal to something involving t squared plus 3 and an integration constant. Now, the next step here is to use some conditions that you were given in the statement of the problem that allow you to solve for t. And I go back and I look at those conditions that you were given that will help you find your integration constant. So I say here, find your integration constant by incorporating these facts. And it said at time equals the square root of d, the tank holds 9.b gallons. So once you find this constant, you can replace v of t in your equation. And what I mean by that is you now have v of t equals something here involving t squared plus 3 plus the constant. This value here, the square root of d, can be substituted on the right side of this equation for t, and the v of t can be substituted using the fact that the tank holds 9.b gallons. So whatever your b happens to be, let's say if it's 3, 9.3 can be substituted for v of t. At that point, the only variable you'll have left in this equation is c, and then you can solve for c, and you will have v of t equals something and no constants involved. You will have solve for c, and you will have a real number there. The final step in this process is now you can find the volume for some value of time, which is, in your case, it's going to be your value of c from your calculus identification number. So essentially at that point, you're substituting your value of c into v of t, and you can find the volume at a certain time of t, which is your value of c. So again, this is our first shot at integral calculus, and I hope this is enough to get you started. If there are any questions, you can drop me a note on the board. As we always do, let's just take a quick look at the rubric. Again, 3 components here, looking for your best effort on your first attempt. If something still needs to be cleaned up, obviously I'll put that instruction for you on the discussion board. You can take a look at that, and then finally a clean and professional document, or posted right into the discussion board with something that uses an equation editor. So I hope this is helpful. And again, welcome to Integral Calculus in the last 3 weeks of the course. I hope this is helpful, and if there's anything I can do for you, let me know. Have a great day.